Hello everyone, welcome to C Programming with Abhijit Sathe. Did you know, programming and coding are actually different? If you are new to programming and not having good knowledge of C programming language, you are watching correct video. Programming is the whole process of solving a problem using a computer. Coding is just one step in it. Remember, you cannot learn programming by just copying and pasting code. You need to understand how it works. Let's get started. This is a brief representation of session for our website www.questionbankos.com. Today we will learn how to think like a programmer and write C code. Programming is a process of solving problem on machine by writing correct and efficient code. It involves 5 important steps. In this short video we will discuss all these 5 steps, and also we will write program to calculate factorial using 3 different ways in C. You know, one problem can be solved by many different ways, out of which 2 are most common: iterative and recursive. We will see both logical methods in this video. 5 steps in programming are as follows. Step 1 is identification of problem, which is also known as problem definition. Step 2 is design and analysis of algorithm, which involves writing very basic, clearly defined instruction, which can be executed on machine to produce desired result. Step 3 is translating algorithm to statements of programming language like C, and this step is known as coding. Step 4 is testing and debugging your code on machine to verify its output. Rectify the code and if necessary algorithm, to ensure correct output. Step 5 is deployment and maintenance, which is usually not followed by beginners like you. It is basically installation of program on target machine or device. We will use an example of GST bill for further discussion. To effectively build our solution, we must first clearly identify the problem. Businesses face significant challenges manually calculating invoice net amounts and GST components. To solve this, our system requires 2 main inputs: the base price of the product and the applicable GST rate slab, ranging from 5 to 28%. Our expected final output will automatically generate the total GST, explicit CGST, SGST, or IGST breakdowns, and the final gross amount. As a key constraint, the system must precisely split intrastate sales equally between central and state taxes, while applying full IGST exclusively for interstate transactions. Problem definition is a very important task. We cannot move to the next step unless we have clear and complete knowledge about the problem to be solved. You can see in this example of GST bill generation how crucial is understanding input and output specifications and business constraints to write a correct program. Moving to the design and analysis phase, we must select existing algorithm or design new efficient algorithm from scratch. This development process requires a careful trade-off between execution time and memory space. To achieve optimum performance, we utilize appropriate data structures. This includes linear types like arrays and queues, non-linear types like trees and graphs, and built-in language structures like classes. Ultimately, selecting the right data architecture ensures our advanced GST calculation pseudocode handles transactions with maximum efficiency and minimal lag. Now we transition from planning to the actual implementation phase, coding. This step involves converting our designed algorithm into clean, executable statements using our chosen programming language. The practical coding process focuses on translating logic into clear structures by utilizing variables, loops, and functions. Crucially, this phase demands rigorous debugging to identify and rectify syntax and logical errors as much as possible, ensuring stable and reliable performance across all target devices. It is critical to note that coding is usually executed within a robust development environment. This workstation, or IDE, is typically entirely separate from our final target machine or embedded device. Depending on system requirements, languages like C, C++, Java, Python, Go, or Rust are selected. You have chosen C programming language to learn is a good choice at first place. Did you know? All popular operating systems including Android are developed in C. Next we move to testing and debugging. This phase systematically evaluates the program's behavior against a complete matrix of both valid and invalid input scenarios. Crucially, we must execute the application directly on the actual hardware device within its expected, realistic operating environment to catch real-world issues. The feedback from this loop is highly actionable. If failures occur, we use these insights to modify the core algorithm, which directly drives corresponding updates back into our codebase. Reviewing our complete development pipeline, we arrive at the critical final stage of testing and debugging. Here, our primary focus is comprehensively testing the software against all possible input boundaries. This phase is designed to identify 2 main types of defects: syntax errors that slipped past the coding phase, and deeper structural logical errors. If defects are found, we systematically trace them back to the source. If necessary, we modify the core algorithm design, which iteratively triggers corresponding updates to our underlying codebase. We now reach the final and most critical phase of our software development lifecycle: deployment and maintenance. During the initial deployment step, the fully tested and validated application is packaged, transferred, and installed directly onto our targeted production server or field hardware, such as an active POS terminal. Once the system is officially live, continuous maintenance begins. This long-term process is vital for fixing newly discovered bugs, deploying code updates for shifting tax regulations, and optimizing system performance to ensure the application remains highly reliable under real-world operational demands. We hope you have understood all steps involved in programming. To read detailed blog, you can visit our website. Now let's move to C programming to see how we can implement factorial program. Let's examine the logic for calculating a factorial using an iterative approach. Our algorithm first accepts an input value n from the user. We then initialize our tracking variable fact to 1, which correctly handles the foundational mathematical rule that 0 factorial equals 1. Now iteratively we keep on multiplying variable fact with I. You know, factorial calculation is continuous process of multiplying factorial of 0 with 1 gives 1 factorial, and further multiplying it with 2 gives 2 factorial. This goes on till we reach to our input value n. Now let's move to recursive process of calculating factorial, in which we reduce our problem to simplest case where solution is directly available. You know, factorial of 0 is 1, so to calculate factorial of 5, we reduce our problem to factorial 0, which is 1, then we use this value to calculate factorial 1, we use the result of factorial 1 to calculate factorial 2, and so on. Some well-known problems can be solved only by recursive logic on machine. We will discuss them later in some other video. Building on our algorithm, we now implement the iterative factorial solution using standard C programming. Inside the main function, we declare our integer variables and initialize fact to 1 to handle our base case. Next, the program requests a non-negative integer from the user using scanf. Notably, the code includes a validation check. If a negative value is accidentally entered, an if statement safely alerts the user and dynamically converts the number to positive by multiplying it by -1. Finally, a standard for loop executes from 1 up to n, progressively updating the running product. The final result is outputted via printf, and the terminal below highlights compilation using the GCC compiler. Looking closer at our source code, the essential preprocessor directive #include stdio.h. It is a library file that contains many input and output functions, out of which we are using printf and scanf in outcode. Do remember, C programming language does not include any input or output statements like other programming languages. We will discuss about this in detail in our next video. Directing our attention to line 5, we declare our first integer variable, named n. In programming, this variable acts as a human-readable identifier for a specific, isolated block of memory allocated to our program by the underlying operating system during execution. The primary structural purpose of this memory slot is to securely store the integer value provided directly by the user via the command line interface. Once saved, this stored input serves as the definitive upper target or boundary that our iterative algorithm processes to successfully calculate the final factorial value. Next, on line 6, we declare our second integer variable, which uses the identifier name I. Structurally, this variable serves a vital role as our primary loop counter or index during the iterative calculation phase. The program uses I to sequentially generate every single integer value, starting from 1 all the way up to the user's input, n. In each progressive step of the loop execution, the current value held by I is multiplied directly into our running product accumulator. A general standard practice of naming variables used in loops as I, j, and k. When operating system allocates memory to our program, it has an address which is a number. Remembering number is difficult for us. Programming language allow us to access them using name, also known as identifiers. This repetitive processing ensures that every sequential factor is properly included to arrive at final result. We declare and initialize our accumulator variable, named fact. This key identifier used to store both our intermediate calculations and the final result. We explicitly initialize fact to 1 to satisfy the mathematical rule that 0 factorial equals 1. Directing our attention to line 8, the program utilizes the standard library function printf to display a message on the screen. This instruction explicitly prompts the user to enter any non-negative integer. By outputting this clear text string before the program pauses for data entry, the application creates a clean user interface. This critical step guides the user on exactly what data type is expected, ensuring predictable interaction before the program captures the value into system memory. Because we include library file stdio.h, printf and scanf are available to our program. Moving to line 9, the program invokes the standard library function scanf to actively capture user input. The formatting string %d specifies that the data must be interpreted strictly as integer value. The ampersand operator placed before our variable name n tells the system to pass the exact memory address location of n to the function, ensuring that the integer provided by the user is correctly written directly into memory slot identified by n for later calculation. Next, on line 10, we encounter a conditional if statement designed to validate the user's input before processing. Because a mathematical factorial is strictly undefined for negative integers, the program must evaluate whether the value stored in variable n is less than 0. If this conditional expression evaluates to true, execution routes directly inside the curly braces. Here, the program alerts the user about the invalid input and handles the error gracefully by multiplying n by -1, dynamically converting the negative entry into its positive absolute equivalent so the application can safely proceed with calculation. Examining lines 12 through 14 inside our conditional block, we see exactly how the program handles invalid inputs. First, the application uses two consecutive printf statements to explicitly warn the user that a negative number was entered and that it is being programmatically corrected. Then, line 14 executes the core recovery math, n equals -1 times n. By multiplying the negative integer by -1, the code leverages basic algebraic principles to dynamically overwrite the variable with its absolute positive equivalent. This defensive programming step ensures our main calculation loop receives a clean, non-negative value to prevent infinite cycles or mathematical runtime errors. At line 16, we find the for loop statement, driving our iterative logic. This looping block initializes the index variable I to 1 and executes sequentially until it reaches the user's target input, n. Inside the loop on line 17, the program progressively multiplies the current index by our running total accumulator, fact. This repetitive structure ensures every sequential integer is multiplied together to compute the complete factorial answer. For loop and the statement within it is the exact translation of iterative algorithm we have seen before. Actual coding adds to many other statements, depending on programming language. C programming language has many looping constructs. For loop is one of them. We can use for loop in a situation when we know the possible starting value and ending value clearly for iterations. Finally, we reach line 20, which contains the statement, return 0. In C programming, the main function is defined with an integer return type, meaning it must send a whole number back to the operating system upon completion. By returning the value 0, our program officially signals to the host system that the code has executed successfully from start to finish without encountering any critical runtime errors or crashes. This standard exit status code acts as a green light, allowing the operating system to safely terminate the active process and immediately clear out its allocated memory resources. If we have to terminate our program abruptly due to some logical error, we can return the value 1. Did you notice problem in this program? The problem with this implementation is that we have to rewrite same code again and again to calculate factorial for different other problem. We need a mechanism to write code once and use it anywhere anytime. We can accomplish this by using concept of function. Now we make our code much cleaner by putting the whole factorial calculation into its own separate block, called a function, starting on line 4. By grouping these steps together, we create a tool that can be used over and over again. Instead of typing out the same long loop every single time we need it, we can just call this function with one simple line of code, which saves time and keeps our program easy to read. C is a procedural programming language in which program is a set of small functions. Let's look at a new way to calculate factorials using recursive function. A recursive function solves 5 factorial using the algorithm on the right. First, the program checks if our number equals 0 to return 1. If it is larger, it follows the else rule, multiplying the current number by the factorial of itself minus 1. As we have seen earlier, recursion winds the problem down step by step from 5 all the way to 0. Once it hits 0, the answers pass backward to solve the main problem. Recursion simply means a function calls itself inside its own body. Look closely at lines 7 and 8. Recursive function is the exact translation of recursive algorithm we have seen just now. Thanks for watching video patiently till the end.